Hello and welcome back again. So this week we are starting function generators and oscillator circuits. Uh, we have seen one function generator. We shall take a couple of more examples, popular examples, and you shall see that there is a common underlying similarity in all these circuits. So if you understand them, one or few of them well, you can generate, you can make your own circuits, not very difficult. So today now we shall take up a popular circuit called 555 timer. This also comes in a compact integrated circuit form, this IC 555 timer. You can also make it, you can also realize this circuit using op amps. Once we study it, it is very simple. Okay. So, the topic is IC 555 or 555 timer. So, this is what this is a oscillator circuit. This can be used as an oscillator circuit, and we can generate a square wave using this, okay, just like the previous function generator we have talked about. Using this circuit also we can also generate square wave or rectangular wave to be precise. So, let us see, this is made up of mainly two comparators. Okay. Once again, do not please try to memorize it, try to understand it. If you understand it, you can always recall and reproduce it on your own, you do not have to memorize it. So, just I will take two comparators and one potential divider. So, let us take two comparators. These are op amps. They will have two inputs, plus minus, one output, and a potential divider which has three equal voltages, equal resistances 1, 2 and 3. This side is 0 volt, this side is positive, we call it VCC. Okay. This is a positive voltage applied and this is 0 volt. This is R, this is R, this is R. So, what is the voltage here? The voltage, this voltage will be VCC by 3, 1/3 of VCC. This voltage will be 2 VCC by 3, 2/3 of this voltage. The task of these two comparators is to compare another voltage which I haven't drawn, or let me just draw it. So, another voltage, okay, call it VC. So, there will be another voltage coming from somewhere, something. This voltage will be compared against these two levels. Okay. So, we have to compare this voltage whether it is higher than this 2/3 of VCC or is it lower than this level. This is what we have to do, and to compare with this we have this comparator, and to compare with this we have this comparator. Say this comparator will tell me if the VCC is lower than this. So, what we can do, let us connect this to the plus terminal, and let me connect this to the minus terminal. So, this voltage will tell me if this is higher or lower than this VCC, VCC by 3. Okay. So, now this will be high. So, let me write this will be high, this output will be high if, when this will be high, if this is low, if negative input is low, that means if V c is less than V c c by 3, okay, and that means also this will be low if V c is greater than V c c by 3. This is what this will tell me. Okay. Similarly, I will connect this comparator, so that this comparator tells whether this is higher than this or not. Say I want that the output to be high if this is what I want. Okay. I want this is to be high if V c greater than 2 V c c by 3 and low if V c is less than 2 V c c by 3. So, what I have to do then, I have to connect the plus terminal to the V c c and the minus terminal here. So, if this V c goes high, then the output will be high, right. So, I mean, once I complete this circuit, after that you will see that you actually do not have to remember anything. You could have taken all these opposite logics. You could have taken that this is low if this is greater, this is high if this is, and so on. Okay? And accordingly, you can complete this story and complete the circuit. So, make your own choice, think and choose. Okay. Now, what I will do, I will take a flip-flop, SR flip-flop. SR, these are the two inputs. I can take two outputs, Q and Q bar. This is SR flip-flop. Let me connect this to the two inputs. Okay. Once again, you could have connected this to a reset and this to set. There is nothing quite secret about it. You can still complete this story in that way. Okay. You have to adjust things accordingly. Okay. So, I connect this to S and R arbitrarily. So, then what can I write about this? Let us say when this will go high, when Q will be high, Q will be high if I have a set signal coming here. Okay. And when I will get set signal, I will get set signal if this is high, and this is high if V c goes above this. So, this will be high when V c goes above V c c into 2 by 3. Okay. If V c goes above this, then this will be high, and this will be low if I have a high reset signal. That means this should be high, and that this will be high only if V c goes below this threshold, below this point. So, this will be low when V c goes down. So, goes down V c c by 3. Okay. So, if this voltage is changing with time, and if it goes above, so there are two levels, you can see there are two voltage level. If this goes above this level, then here the output will be high, and if this falls below this level, then the output will be low here. Okay. So, this is okay. So, these are the main ingredients of this flip-flop, two comparators, one potential divider. Now, what I will do is this. I essentially want oscillating voltage. Okay. So, I will also take this voltage changing with time. For that, what I will do, I will take a capacitor call it C. I will take some resistances, few of them you can take, call them RA, RB, and this side I will connect to VCC, positive voltage. This side I will connect to ground. So therefore, what will happen? The moment I make this connection, current will start to flow in through this resistance and charge this capacitor. Therefore, this potential will increase, and this I will connect to VC. Now you possibly know why I call it VC. This is the capacitor voltage, VC. So the moment I complete this circuit, this potential will start to increase. Therefore, this potential will start to increase also. And what I will do, I will take a kind of switch, a transistor based switch, and I will connect that to this like this. Okay, let me draw it in a different color. So I will have a switch. Let me first draw it like this. So if you see, if I keep this switch open, if this is open like this, then okay, it will just charge the capacitor. Current will come like this from top to bottom, and it will increase, potential will increase. But if I close this switch, then what will happen? Then this is connected to ground. This is at zero potential. So if there is any charge in this capacitor, that will discharge and go to ground. So this potential will drop. Okay. So if I connect this switch, the capacitor will discharge to the ground. And if this is open, then current will come from VC and will charge this capacitor. Now I cannot take a manual switch like this. I will take a electronic switch. Let's take a transistor based switch. Okay. So if I give a positive or high voltage here at the base, then this transistor will act like a short circuit, and so the switch will be on, so current will flow like this, capacitor will discharge. And if I give nothing at the input or low voltage at the input, then if the input is low, this base voltage is low, then this will act like an open circuit. So this is not connected, so the capacitor will charge. Now what I will do is this. I observe that this voltage increases. So this is off, then this voltage will increase, which will make this output high after a while. Okay, so I will connect it to this. Okay, because you see, say initially this is off. If it is 0, then current is coming and this voltage is increasing. If this is increasing, according to this logic, when VC goes above this level, 2/3 of this voltage, then this output becomes high. So this will be connected to this, and then this transistor will be short circuited. So therefore this switch will be on and the capacitor will discharge through this. This potential will start to drop and this VC will start to go down, and as it goes down, at some point, this comparator will tell me that VC is lower than this threshold. So this will trigger the reset and this output will be low, and once this is low, this will be off, this transistor will be off, and if this is off, then it will start to charge again. Okay. So, this way it will keep oscillating between charging and discharging. Okay. So, let me just write the essential story in few words. Say, if call this transistor T1, if and call this voltage base voltage B1. Okay. So, this is B1. So, this voltage is VB1. Okay. Say if VB1 is low, then T1 is off, then capacitor C will charge through RA and RB, these two resistances, and therefore Vc will increase. Then when Vc, this voltage goes above this level, when Vc goes above this level, 2 Vcc by 3, call this comparator 1. So, call this V comp 1. Okay. Then V comp 1 will be high and flip flop will be set and Q will be high. Okay. And then what will happen? So, now Q, I mean the output VB1, because this is the same thing. Now, VB1 is high. So, T1 is on. So, C will discharge through RA only, discharge through RA. RB will not be there. The current will directly go to ground through RA, discharge through RA, and so Vc will decrease. And the last thing, when Vc goes, so Vc is now decreasing. So, when Vc decreases below this level, Vcc by 3, okay. When this goes below this by 3, okay, divided by 3, then call this V comp 2. V comp 2 will be high, and if this is high, then reset will be triggered, Q will be reset. Q will be reset to 0 or reset to low. Okay. This way it will oscillate forever. Okay. I hope the functionality is clear. And so, next thing what we can do, we can talk about the frequency of this circuit. Okay. So, the question, what is the frequency? Or what is the time period? Okay. Okay. And we should be also able to draw the waveforms at different points, this voltage, this output, etc. Okay. I hope you can still read this because you know now what actually is there. Okay. Okay. So now let's draw the waveforms. Say let's start with this VB1, and once again to start with we have to assume some initial value. Say this is initially high. So this is initially high, so we start with some high value, and then let me take this as Vc, the capacitor voltage here. Okay. So if this is initially high, then the capacitor is discharging through Ra. So if the capacitor voltage is something, it has some initial value, once again this is an assumption that this is the initial value, then it will discharge, okay, and it will go towards zero voltage. Okay. So I start from here and it will go towards the zero voltage. Okay, exponentially, because this is a RC circuit. This is just like this, right? Capacitor C, then in series we have Ra, and then this is grounded. That means these two are connected. So this will discharge with the time constant RAC. This is going down towards zero. But will it reach zero? It won't, because something different will happen at the moment when it reaches the level VCC by 3. So this height is VCC by 3. If this is VCC by 3, then somewhere here I will have also, let me draw this level as VCC into 2/3. This is VCC into 1/3. Now the moment the capacitor voltage comes here, story will change. Why? Because this voltage is lower, so this op amp will be triggered. This will say the output is here high, reset will be triggered, so this will be low. Okay, if this is low, then this switch will be off. Okay, so after this moment, the switch will become off, and if this switch is off, then the capacitor will start to charge instead of discharging, because this part is not connected. It is connected like this. Okay, this Ra, then Rb, Ra. This is no longer there; it's open. But here I have the voltage VCC and ground, so this will start to charge. Okay, so it will charge again exponentially, and it will try to go towards VCC. So let this height be same as VCC. So it is trying to go exponentially, asymptotically towards VCC. But will it reach there? It won't, because it will come up to 2 VCC, like this, and then once again the story will change at this point. Okay, why? Because at this point this voltage Vc is above 2/3 Vcc. So this comparator will get activated and it will trigger this set, and therefore this voltage will be high again. This will turn on this transistor again, so it will start to discharge again. So it will start to discharge once again and will try to go towards 0 voltage, but it will not definitely reach that. It will reach only up to 1/3 Vcc. So it will come up to this, and again the story will change. So this is how Vcc will oscillate. Okay, so it oscillates between these two levels, 2/3 Vcc and 1/3 Vcc. And okay, how about this Vb? Okay, let me just call this Vb as V out. Let this be the output voltage of the circuit, okay, which is also oscillating. So let me call this V out. Okay, so here in this part, when the capacitor is discharging, why is the capacitor discharging? It is discharging only because this transistor is on, and it is on only when this is high. So here definitely this is high, and then here it will be low, it is low, and that is why this is off, and therefore the capacitor is charging. Okay, and then here once again it will be like this. Once again, this is not very low level, I mean detail accurate diagram in a sense that, or it's like somewhat schematic, because we are not considering, I mean, what is meant by high or low to this. I mean, which voltage is considered as high or level 1, or which voltage is considered as level 0 for this flip flop. What is the output voltage of this comparator? What is the voltage, exact voltage that should be applied to get this transistor on off? All these exact voltage levels we are not considering in detail. We are only considering whether it's when it is high, when it is low, how it will oscillate. So we are looking at it from a abstract level, not somewhat abstract level, not very detailed. Okay. So I mean, for example, should the supply voltage to this op amp be plus minus 12 volt? Is it? If so, then this output will be plus minus 12 volt. But for a digital circuit, maybe 12 volt is not acceptable. Okay, so those details you ignore right now. Okay, so fine. So the original question was to find the frequency. Okay, so we have to find the time period. Which is the time period? The time period is from here to here. This is the time period. So we have to find this time, and for that we have to find this to time. Call it T off and call this T on. T off is the time when the output is off or low. T on is the time when the output is on or high. Okay, so let's find T off. Let's find how much is T off. So you see the capacitor is starting. So Vc starts from VCC by 3 and it is trying to go to what value? VCC, okay, the supply voltage. Okay, if nothing is stopping this capacitor from getting charged, if this transistor is not there, then it will go to the full value VCC. Okay, so this is the target value, target voltage. This is the initial voltage. Okay, and then the so this is the target. Okay, so how far is the destination, or the difference between the initial and the target, or I mean this gap between this and this, target and initial value, target minus initial. This is VCC minus VCC by 3 is same as 2 VCC by 3. Okay, this is how much it wants to go. Okay, this is how much it wants to go, and therefore the VC capacitor voltage, you can write it target minus this. So what will happen? Finally, this term will be 0. So final value will be target value. Okay, as t tends to infinity, and initially when this is 0, this is 1. So this is 1. So this part is not there. Then this target cancels, and we will have only initial value. So this is how the capacitor voltage changes. Okay, so let's write it this way. Then target is VCC minus this is 2 VCC by 3 and e to the power minus t by tau. What is tau? This is the time t off here. The capacitor is charging. So it is charging through RA and RB, both of them. Okay, so the total resistance in this circuit is RA plus RB. So this is RC. So and R is RA plus RB multiplied by C. Right. This you could have also derived, formally, like the way we do using differential equations, etc. But this is how you can also remember. And if you haven't studied differential equations or you do not know these transient formulas, you can remember it in this way. Okay. So finally, it will be the target value when this will be 0, and initially it will be this is 1. So target cancels, and the initial. So this is how the voltage changes. Okay. Now we have to find how long will it take to go from initial value to this 2/3 VCC. Okay. Say this time, if this is this t equal to 0, this time is t equal to t of, sorry, not this time, this time okay. If this is t equal to t off and this is t equal to t0, so this is the time required for the capacitor voltage to go from 1/3 VCC to 2/3 VCC. So then we write, starting from this equation, VC capacitor voltage at this moment t equal to t off, this will be the initial value e to the power minus t by, let me write tau only, I'll put the value later. Okay. And so at this moment we know the value is 2/3 VCC. So this I write is equal to VCC into 2/3, because VC T off at this moment this value is 2/3 VCC, right. So now from this will imply my target is to find the value. Oh, here also this time will be T off. My target is to find the value of T off. Okay. So let me equate this this with this. So this implies VCC and 2/3 VCC, that will cancel somewhat, and I will have only VCC by 3, and this I will take on the other side, 2/3 VCC e to the power minus t off by tau. Now from this VCC goes away, 3 goes away, only this 2 is required. So I can write that 1/2 is equal to e to the power minus t off by tau. From this 2 is equal to e to the power t off by tau. From this t off by tau is equal to, let's take log ln 2, log on this side, log on this side, and from this we write t off is equal to ln 2 multiplied by tau, and tau is nothing but C times RA plus RB. So this is the off time. Okay, so now we will similarly find the value of on time, and then we will, so on time is this time or this time, then we will add t on and t off together to get the total time period. আচ্ছা, একটা তো 10 হয়ে গেছে, আপনারা তো যাবেন মনে হয়, এখানে এটা তাহলে পজ করি, কালকে এখান থেকে স্টিচ করে দেবো। না, আপনি যদি অ্যালাউ করেন আমাকে, তাহলে আমি কন্টিনিউ করব। হ্যাঁ, আর ধরুন 10 মিনিট, 10-12 মিনিট লাগবে, তাহলে আমি কন্টিনিউ করছি। হ্যাঁ, ওকে। সো লেটস নাও ফাইন্ড সিমিলারলি the time t, this is t on, so for this let's first write how this voltage changes in this period. Okay, so it starts from 2/3 VCC. Okay, so in this period, in this on period, VC starts from 2 VCC by 3, and target voltage is, so it's trying to go to 0, so target is 0. So then we can write once again VC t is equal to, just use this idea, target minus initial e to the power minus t by tau, call this tau on time. This is the and this is for the on time. Okay, similarly the previous one I should better call it tau off. This is tau off, this is tau off, off. Okay, time constant tau off and time constant tau on here in this case. Okay. So, and then let us put the values. Target value is 0 and this t, okay. So, this t is actually the time measured from this moment. Okay. So, I am re-initializing the time at to 0 here to do the estimation here, or if you do not like that, then if you still want to keep this as the origin for time, so let me then subtract this previous value t off. So, you can write this t minus t off, but I think this is complicated. Let me just write t only, this is simpler, and noting that t is measured from this point, call this A, from point A. Okay. So, then 0 minus target minus initial is how much? 0 minus 2, so this will be again minus 2 VCC by 3 e to the power minus t by tau on, minus minus goes away, 2 VCC by 3 e to the power minus t by, what is the value of t on? T on is the time constant in this period when this switch is on, this time, this discharge time, this is on. So, only RA is there, RB is not there, RA is there in series with C. So, this I will write RA times capacitance C. Okay. So, this is the value of Vc, and now let us call this time t equal to t on, okay, starting from this value, okay, starting from this value. So, this is the time t equal to t on, my target is to find this value, because I want to find this gap, this time of on time, and for that I have to find this time, the instant when this goes down below VCC by 3. Okay. So, if we assume that Vc at t on, it goes to VCC by 3, then let me just write the value of this by putting t on in this expression. This becomes e to the power minus t on by RA C. Okay. Now, this is simple to find t on. So, once again you can cancel VCC 3. So, I have only 2, this 2 will become half. If you bring it on the other side, is equal to e to the power minus t on by RA C, and from this once again if you do similar calculations, you will find that t on is equal to ln 2 multiplied by RA C. Previously it was this, it is very similar if you do the calculation. Okay. So, then the total time period is t on plus t off, and let me just put the two values. One of them is RA C multiplied by ln2 log 2, another is RA plus RBC multiplied by log 2, and the frequency is 1 over time period. And if you want to control the frequency, change the frequency, so you can change this RA, RB and C to change the frequency. You can change only RA or RB to change only say on time and only off time, okay, and change the duty cycle, that is the ratio of on and off time. So, you can change with the shape or the duty cycle of the waveform output by changing RA, RB or both. Okay. Thank you.